So, we shall continue from the process where we left, namely the representation for the angular momentum operators x, y and z with in the basis set for j is equal to 1. And the basis set for j is equal to 2 is identical in principle for the calculations, but there are 5 basis functions and the basis set is given by this 5 basis functions 2, 2, 2, 1, 2, 0, 2, minus 1 and 2, minus 2. Therefore, following the same argument that we had, if we write j plus as a 5 by 5 matrix, remembering that the basis functions were ordered in this form 2 minus 1 and 2 minus 2, and in the raw state they were ordered this way 2 2 2 1 2 0 2 minus 1 2 minus 2. You can see that this element is 2 2 j plus on 2 2, this will be 0, and j plus acting on 2 1 will give you a 2 2, therefore, this is non-zero, and all the others will only step up once, but this is already more than one step away, therefore, this is 0, this is 0, this is 0, and j plus operator is stepping up, therefore, 2 1 to 2 2 is not possible, j plus on 2 2 is 0 and diagonal element is also 0, and so what we have is this, and the other two are also 0. These are 2 steps away from each other, the j 2 1 and this is for example 2 minus 1 and this is 2 1 to 2 2, 2 minus 2, 2 1 j plus 2 minus 1 and 2 1 j plus 2 minus 2. That is this element and this is this element, and they are obviously 0. So, if you continue this, you can see right away the diagonal off diagonal form, that this is what you will have, and all the 5 elements are 0 because none of them will give you 2 minus 2 when the j plus acts on them. So, this is 0. Therefore, you have to calculate 4 matrix elements only, and you have to use the same formula that we had, j plus on 2 1 is going to give you h bar. In the last representation I have omitted the h bar, so you must put the h bar here and you must put the h bar here in the representation of this angular momenta, and likewise this is also h bar by 2 and this is minus I h bar by root 2. Please keep this in mind, sorry. Yeah, and if we do the same thing here, j plus on 2 1, you have h bar j minus m, which is 1, and j plus m plus 1 is 4, therefore, it is 2 and then the state is 2 2. Therefore, the state 2 2 acting on this will give you 2 2 h bar 2 acting on 2 2. So, the answer is 2 h bar. Okay. Likewise, the element 2 1 j plus acting on 2 0 gives you, this is square root of j plus m, which is 2, j plus j minus m, which is 2, and j plus m plus 1, which is root 3. Therefore, this gives you root 6 and the state will be 2 1 after the action of this, and therefore, it is h bar root 6. 2 0 j plus on 2 minus 1 will give you again the same thing, j minus m will be 3 and j plus m plus 1 will be 2. So, it will give you h bar root 6. 2 0 2 0, and this will also be h bar root 6, and the last is 2 minus 1 j plus on 2 2 2 minus 2, and you can see that j minus m is 4, j plus m plus 1 is 1, therefore, this will give you 2 h bar 2 minus 1, the state 2 minus 1 and 2 h bar. So, the matrix element for j plus is immediate, that it is h bar 0 2 0 0 0 0 0 root 6 0 0 0 0 0 root 6 0 and 0 0 0 2 and it is 0 0 0 0. Therefore, you can see the matrix for j minus is the Hermitian adjoint. Of course, these are real numbers, therefore, you have simply 0 2 0 0 0, the adjoint, the transpose of the row, and the transpose of the second row is 0 0 root 6 0 0, the transpose of the third row is this, and the transpose of the fourth row is 2, and the transpose of the fifth row is all 0. So, this is j minus, and therefore, you can see immediately that j x is 1 by 2 times j plus j minus, and so you can see all the elements which are not 0 0 2, and of course, this is j x is a Hermitian matrix, you can see it right away, and this is root 6 0 0 0, and you can see that this is 0 0 0 and this is root 6. So, you will have 2 0 root 6 here 0 0 0, and this element is root 6 0 0, therefore, it is Hermitian, the transpose of that will be root 6 0, and this will be 0, and this is 2 2 1 2 3. Oh, okay, I have an extra column here. I was wondering what happened. Okay, so 0 2 0 0 0 2 0 root 6 0 0. Yes, this is correct, and now this will be 2 and this is 0. So, this is j x. J minus is minus I by 2 j plus minus j minus, therefore, you can write this as minus I by 2, and this component is all j minus. Please remember, this is all j minus component, this is all j plus component. The j plus component remains unchanged, of course, minus I by 2 has been taken out, therefore, j minus can be written the jz, sorry, jy can be written immediately as this way, and so what you have is 0 2 0 0 0 minus 2 0 root 6 0 0, and then you have minus root 6 0 root 6 0, because all of this is j plus, and then the minus is, there is a minus 2 here. Let me write the fourth one. This is 0 0, this is 0 0, and then you have 1 2 3 4 5, all these things are there. So, you have root 6 0, and you have a root 6 here with a minus sign, and you have a minus 2 here, and this is what you will get. Okay. So, this is all from the, sorry, this is all from the j minus with a minus sign, and all of the others are from the j plus with the plus sign. So, jx, jy, and of course, jz is very simple because it is diagonal, and it is simply the m value. So, Jz is immediately written as m being 2 0 minus 1 minus 2 1 0 minus 1 minus 2. So, you have 2 1 0 minus 1 minus 2, and so you have these zeros of all these things 1 2 3 4. This is diagonal. So, you have 1 2 3 4. There are 5 of these, and that's the Jz operator. Once you know these operators, it is possible for you to write Jx squared, Jy squared, Jx Jy plus Jy Jx. This is a Hermitian combination, Jx Jz plus Jz Jx, and Jy Jz plus Jz Jy. You can simply multiply the matrices that you have to get the operator form of the matrix form of the operators given here, and also Jz square. Okay. So, this is a very simple way of representing angular momentum matrices for the angular momentum operators using the basis functions which are diagonal for the operators which are diagonal, or the J square operator and the Jz operator. Okay. This is problem 4. Okay. Now, theorem to determine the upper bound to the ground state energy of hydrogen, and using a trial wave function exponential minus alpha r, where alpha is the variation parameter. The hydrogen atom Hamiltonian is minus h bar square by 2 m del square minus E square by 4 pi epsilon naught r. Psi is given as e to the minus alpha r, and the expectation value you are supposed to calculate as a function of the parameter alpha is for the operator from 0 to infinity r square e to the minus alpha r, and the hydrogen atom Hamiltonian that you need to worry about is only the radial part minus h bar square by 2 m r square d by dr r square d by dr acting on e to the minus alpha r dr. All the angular parts, the integral gives you only 4 pi, because the function does not contain any angular variable. Therefore, the rest of the Hamiltonian containing the angular variables acting on the exponential minus alpha r will give you 0. Therefore, there is no need for them, and the integration of the angular variables over 0 to 2 pi and 0 to pi sin theta d phi will give you 4 pi. So, this is all that you have to calculate. This is for the kinetic energy, and a corresponding term that you have to calculate is 4 pi 0 to infinity r square e to the minus alpha r minus e square by 4 pi epsilon naught r e to the minus alpha r dr. Okay. This is the expectation value for the energy E using the Hamiltonian and the wave function, the exponential minus alpha r. Therefore, this is a function of alpha. In fact, you would see that once you calculate the E of alpha, I would only write 2 or 3 steps, because it is again a straightforward integration problem. So, you should be able to calculate this quantity. For example, 1 by r square d by dr. Let us leave the 1 by r square out, because that anyway gets cancelled with the r square part of the integral itself. So, if you write this d by dr, r square d by dr of exponential minus alpha r, then what you have is it is a d by dr r square minus r square alpha e to the minus alpha r. and you can see that the second derivative gives you this result minus there is also a minus 2 r alpha e to the minus alpha r, and then you have a plus r square alpha square e to the minus alpha r. So, this is everything that is in the derivative form, but for the minus h bar square by 2 m r square. Okay. So, you can substitute that and do the integral. The integral that you need to do are the following: r e to the minus alpha 2 alpha r d r from 0 to infinity, and the other integral that you have to do is 0 to infinity r square e to the minus 2 alpha r d r. This integral is a standard integral. Please recall that we used this in one of the problem sets earlier, that this is x raised to n e to the minus a x dx is n factorial by a raised to n plus 1. Therefore, this will give you the integral from 0 to infinity r e to the minus 2 alpha r dr will give you n is 1 and a is 2 alpha. Therefore, you will have 1 by 2 alpha square, which is 1 by 4 alpha square, and the other integral that you will get, namely r square e to the minus 2 alpha r dr from 0 to infinity is n is 2. Therefore, it is 2 factorial, which is 2, divided by a is minus 2, a is 2 alpha raised to n plus 1 is 2 alpha cube, and therefore, it will give you 1 by 4 alpha square, 4 alpha cube, sorry, 4 alpha cube. These are the only two integral details that you need to know in order to calculate this, and if after some time, maybe about half an hour, if you do not make any mistakes, or probably less than that if you are fast enough, the integral that you calculate, of course, there is also one more item that I have missed here. The wave function should be normalized. Therefore, you need to do psi star psi r square dr d theta sin theta d phi. This should be set equal to 1, and this will be, the answer to this will be 4 pi, that comes from the angular integration, and the integral is 0 to infinity r square e to the minus 2 alpha r dr, and that would give you, you remember this gives you 2 factorial divided by 8 alpha cube. Therefore, the answer you will get is pi over alpha cube. Therefore, psi is square root of alpha cube by pi e to the minus alpha r. This is to be used in your calculation. The result of doing those integrals will be, it is a just algebraic step. So, let me give you the answer, that you will get 4 alpha cube h square by 32 pi square m alpha minus e square by 16 pi epsilon alpha square. Okay. Now, you have to remember to equate this, if this is to be given as a the E of alpha, then you have to set to the dE with respect to d alpha to be 0, and then obtain an expression for alpha. Okay. And if you take the derivative of this expression and you set the derivative to be 0, and you want to minimize this so that the energy is the lowest energy, you will see without any specific difficulty, you would see that alpha is exactly 1 by A naught, the Bohr radius, at which point the energy that you get will be exactly the energy E1, which is minus Hc Rydberg constant, okay, and that is minus 13.6 eV. The very reason for choosing the wave function psi to be exponential minus alpha r for the ground state is to make you recognize that psi, which is exponential minus r by A naught, is the 1s wave function unnormalized. And if it is normalized, you will see that psi is 1 by pi A naught cube e to the minus r by A naught. Recall the similarity of this with the term that you have alpha cube by pi square root e to the minus alpha r. You see that alpha is 1 by A naught, gives you immediately the ground state, exact ground state. Therefore, the wave function that was given to you is for you not to do the whole calculation, but to guess the answer that alpha has to be 1 by A naught, and then therefore the wave function is that, and the energy that you obtain is minus Hc Rydberg constant or minus 13.6 eV. What you might have to also remember is the following formula for the coefficients A naught and the energy E. A naught is pi m E square by h square epsilon naught. This is from the Bohr's model, and the E that you calculate is minus m e raised to 4 by 8 epsilon square h square. This is what you will get when you realize that alpha is 1 by A naught, and therefore the average value E is exactly the ground state. This is the ground state energy. The next problem is an important result in all of quantum chemistry, and it is fairly a straightforward and simple result. First given by the Hellman and working with Richard Feynman, and this is known as the Hellman-Feynman theorem. The problem states that the quantum mechanical eigenvalue for the energy operator is denoted by E, which is the eigenvalue for the operator H. If the eigenvalue depends on a parameter P, such as an external magnetic field or an electric field, verify that the famous result that was given as Hellman-Feynman theorem, namely the derivative of the eigenvalue E with respect to the parameter is equal to the expectation value of the derivative of the Hamiltonian, which is a function of P. This is the angular brackets tell you that this is the expectation value. Of course, what you have on this side is a number, and therefore you must actually get a number here, and H is a Hamiltonian expressed as a function of P, and so the number that you get out is the expectation value. Therefore, the average value of the energy eigenvalue is nothing but the expectation value of, or the average of, the Hamiltonian operator. Okay. This is problem 6. Okay. The energy is written as a function of parameter P as psi star of P, H of P, and psi of P d tau. Let us assume that psi's are the solutions of Schrodinger equation. And it is easier. Okay. So, if psi is a solution, then H on psi is going to give you E on psi. Now, let us calculate the derivative dE by dP. Then what you have is the integral, the derivative goes inside the integral, it calculates the d psi star dP, then it is H of p psi of p d tau, that is the first term. Then there are two other terms which are derivatives which are functions of p, and therefore you have psi star of p dH by dP of psi of p d tau, and the last one plus the integral psi star of p H of p d psi of p by dP d tau. This is the volume space integral. Okay. P is some parameter on which the Hamiltonian depends on, and therefore the expectation value also depends on that parameter. Now, the H acting on P, because H is a Hermitian operator, you know that this is going to give you real values, and likewise the H acting on P is going to give you the real value eigenvalue E. So, if we write the next step, we have E times d psi star by dP psi of p d tau, that is the first term. The second term is obviously psi of p star dH of dP over dP and psi of p d tau, and the third term, taking into account the hermiticity, you have E psi star of p d psi of p by dP d tau. You can see that these two terms immediately add as nothing other than the derivative dE by dP as nothing other than this derivative E, the integral d by dP of psi star psi d tau, and the term which is not disturbed is this one psi star of p dH by dP psi of p dP, and this is of course you know d by dP. P is a parameter that is not controlled by the integral, therefore this is nothing other than E d by dP of the entire integral psi star psi d tau. This is one normalized, or is it a constant, therefore it is independent of p, therefore this is equal to 0, and what you see here is nothing but the average value for the operator called dH by dP, and that is why it is written as the expectation value dH by dP on psi as the dE by dP, where H on psi p gives you E on psi p. H is also a function of p. Okay. A very direct proof or direct verification of the Hellman-Feynman theorem. Let us look at the next problem. This is algebraically it is a long problem, but the methods are extremely simple. I have given an exact calculation in the theory in one of the lectures earlier, and this problem is on the variational method and its use to determine the lowest energy of the state of the particle in a one dimensional box given by the formula given by the state. The state is an arbitrary state psi x comma lambda, lambda is basically lambda 1 and lambda 2 as a variational parametric set of lambda 1 and lambda 2 with two basis functions x square into L minus x and x into L minus x whole square. Okay. Both the wave functions satisfy the particle in a one dimensional box boundary condition. L is the length of the box, therefore I might want to say that somewhere here one dimensional box of length L given by this formula. Now, I have done this precisely for a 2 by 2 matrix problem earlier. So, let me recall the mathematical steps for you to calculate. In one of the lectures earlier, I did mention that one must variationally minimize this determinant H11 minus ES11, H12 minus ES12, H21 minus ES21 and H22 minus ES22. This is what we had said into the coefficients. Here it is of course lambda 1 and lambda 2 is equal to 0. Okay. We wanted to find out lambda 1 and lambda 2 in such a way that E is minimum. Okay. But this is what you have to do in order to get this, and if you solve the determinant you will get 2 eigenvalues, and the smaller of the 2 eigenvalues is the one that is closest to the ground state eigenvalue. Therefore, the calculation involves recognizing the matrix elements and the overlap integrals, and for H11, H12 etc., what is 1 and what is 2? 1 is given by this function, namely, go back and look at the function. This is the first function, x square into L minus x, that is 1 1. The function psi 1 is x square into L minus x. The function psi 2 is x into L minus x whole square. See that, x into L minus x whole square. So, essentially this is the same as your C1 times phi 1 and C2 times phi 2, and H11 is given as the corresponding one, phi 1 H phi 1, and H12 is phi 1 H phi 2 and so on. So, now let us look at this. Therefore, if we call psi 1 as this, H11 is the integral psi 1 H psi 1 dx between 0 and L, and H12 is the integral 0 to L psi 1 H psi 2 dx, and the integral S11 is psi 1 of x square 0 to L dx, and the overlap integral S12 is the integral 0 to L psi 1 psi 2 dx. All these functions are extremely simple, namely psi 1 is x square into L minus x. Therefore, let us just do one element calculation. H11 is nothing other than x square into L minus x times the Hamiltonian for the particle in a box, which is minus h bar square by 2m d square by dx square, acting on the function x square into L minus x dx between 0 to L. This is H11. And what is H12? H12 is 0 to L. The first function is still x square into L minus x, and the Hamiltonian is minus h bar square by 2m d square by dx square, but the second function is x into L minus x whole square dx. Likewise, S11 is the integral 0 to L x square, I think, yeah, x square into L minus x whole square dx, and S12 is the integral 0 to L x square into L minus x times x into L minus x whole square dx, which is 0 to L x cube into L minus x whole cube dx. And likewise, S22 is the integral for the second function, namely x into L minus x whole square between 0 to L dx. I guess we have defined all the integrals that need to be, there is also one more, h22, which is 0 to L x into L minus x whole square times minus h bar square by 2m d square by dx square acting on the function x into L minus x whole square dx. So, we know this, we can calculate all these things are very simple integrals. You have to just sit down and do the algebra, they are elementary integrals. The derivative on polynomials is so easy to calculate that it is possible for you to calculate all these things 1, 2 and h11, h22, and you simply substitute that in this determinantal or in this Hamiltonian matrix and take the determinant to be 0, you get two answers for E. The lowest of the two is the one that is closest to the ground state function. Please remember, the ground state function for the particle in a box is h square by 8 ml square, and the next energy state for the particle in a box is h square by into n square, n is 2, therefore it is 2 ml square. So, you can see that how much E1 differs from this answer and how much E2 differs from the E2 gives you an idea whether your model wave function is approximately is good, or is it really a bad approximation and so on. But of course, in a particle in a one dimensional box we know the solutions, therefore, this is purely to illustrate how to handle such things using known methods. Okay. Therefore, this is a fairly simple enough exercise. I have not solved this into the numerical form because all the integrals that I have left for you to calculate, you can calculate. Okay. Now, I think that brings to the end of this particular video tutorial of 7 problems. And again, as I have said earlier, this time I have not even given the final solutions, therefore, there is enough room for you to sit down and time for you to sit down and work out the answers for familiarizing yourself with the mathematical techniques and also the basic algebraic calculations. Okay. We will continue with the particle with the linear combination of atomic orbitals for the molecular orbital definition for the diatomic molecules, and starting with the hydrogen. I think we looked at hydrogen molecule already, but we will look at the other homonuclear and heteronuclear diatomic molecules. Until then, thank you very much.